Telstra needs to launch a new communication satellite into orbit. We are the scientists who need to keep it in orbit. So how are we going to do it? It seems easy enough, right? Make a communication satellite and then send it into space. While this seems like a good solution, there are two things stopping us from getting into space: air and gravity. We will have to work around these problems in order to get our satellite into space. So let's start with gravity.
What is gravity? Gravity is a force where a planet or body draws things to its center. We all have a gravitational force and exert it, but since the Earth's mass is so big, it actually has a significant impact on us, whereas our gravitational force doesn't affect the Earth at all. Gravity is relevant to this problem, as we need to understand how satellites are able to stay in space. Centripetal force is what we are going to use in order to keep our satellite in orbit. Centripetal force is the force that acts on a moving body in a circular path and is directed towards the center, around which the body is moving. If you had a ball stuck to a string and started spinning it, it would have a constantly changing tangential velocity. If you cut the string while you were spinning it, it would fly off in whatever direction the tangential force was aiming to at the time. The centripetal force is what is keeping the ball from flying far away, as centripetal force is directed towards the center.
Orbit is a curved trajectory that an object takes around another object under the influence of gravity. Orbits can be observed through many celestial objects such as stars, planets, and moons. Orbits can be elliptical or circular depending on the speed and trajectory of the orbiting object. Objects stay in orbit due to a balance of gravitational force and velocity, allowing it to move in a repeated path. If an object moves too fast, it will escape the gravitational pull, and if it is too slow, then it will be pulled into the center and crash. Can be explained by the conservation of angular momentum, which basically says that an object in orbit will remain in orbit unless an outside factor changes the way it moves, in trajectory or speed.
Centripetal force versus gravity. So when it comes to gravity, the same physics apply. Gravity is keeping the ball, or in this case, planet, towards the center, whereas the ball or satellite's velocity is trying to get it to fly off. This means that if we carefully apply enough force to our satellite will go into an orbit. Too little force and it will fall back down, as the gravitational velocity is greater than the tangential velocity. Too much, and our circular orbit will become an ellipse, or potentially leave our Earth's sphere of influence.
For our hypothetical satellite to get into orbit, we will need to utilize the centripetal force. We want a good 2,000 kilometers distance from Earth, in order to minimize the effects of Earth's atmosphere on our satellite. As we begin to get into space, we will have to pay attention to two special numbers: the highest point in our orbit and the lowest point. We have fancy names for these: our apoapsis, highest point, and periapsis, lowest point. To increase our apoapsis, we must increase our tangential velocity from our periapsis, and to increase our periapsis, we need to increase our tangential velocity from our apoapsis. By doing this with our rocket, we can try to even out the satellite's orbit, so that it's circular rather than elliptical.
Our orbit will be at 2,000 kilometers. Unfortunately, air particles can still hit the satellite, even at this height. This will slowly but surely slow down our satellite's orbit. At this height, the satellite will stay in orbit for a couple of weeks or months. To counteract this, we will add RCS thrusters to our satellite to ensure it can boost its orbit periodically and stay away from this atmosphere. Our satellite will also have a communications dish and solar panels to power it.
To get this satellite into orbit, we will use a rocket ship to send the satellite into space, and then get it into orbit. We will fly our rocket's strong boosters to get us high up in the atmosphere, slowly turning our rocket, which is called a gravity turn, to save fuel while getting us into orbit. As each stage of our rocket runs out of fuel, we will detach it so that we can keep our rocket light. Eventually, we will reach space. and increase our tangential force, as we discussed earlier, to circularize our orbit at around 2,000 kilometers.
When trying to go to the moon or other planets, you have to wait for a transfer window so that you can minimize the fuel that is being used. However, with the satellite, we do not have to wait for these transfer windows, so there isn't really a best time to launch our rocket. However, there are better locations to launch rockets from than others. For example, turning the rocket east while launching allows the rocket to use Earth's rotation to get into a geostationary orbit in an easier manner. A geostationary orbit is an orbit around or near the Earth's equator that follows the rotation of Earth. We want to launch our rockets close to our part suppliers so that creating rockets is cheaper and we don't waste money trying to move expensive parts and fuel around the world. While launching a rocket from high up is more fuel efficient, it does cost more money getting the parts and fuel to that location, making it not worth the price.
Our satellite is encapsulated in fairings to keep the satellite from breaking apart as it flies through the air, and also aerodynamic. Once we reach space, we will take these fairings off so that our satellite is exposed, and also so we can save weight. The satellite is equipped with an engine along with RCS thrusters so that it can remain in orbit for extended periods of time. We have solar panels to charge our batteries, along with communication systems to send signals back and forth to Earth. Here is a quick summary of everything we've said so far. Also, if you check the description, there's a poster along with a script describing everything we've talked about so far. Hopefully our solution to getting a communication satellite into orbit, along with keeping it there, helps you understand how satellites work with gravity, centripetal force, and orbital mechanics, along with how we can utilize these to help our satellite get into a stable and circular orbit for extended periods of time.